Drinking a massive 5 liters of soda in a single day subjects your biology to an extreme, punishing stress test. 5 liters delivers roughly 500 grams of dissolved sucrose. Consuming this volume represents a failure of physical processing capacity. You are bypassing the metabolic limits of the human body. This graph tracks sugar concentration in the hepatic portal vein over time. Notice the slow curve of digesting solid carbohydrates compared to the immediate vertical spike of a liquid solution. This sheer velocity creates a concentration spike that instantly overwhelms the liver's metabolic limits. The primary physiological danger of liquid sugar lies in this extreme speed of delivery, which initiates a structural failure across multiple bodily systems. Beyond the physical speed of the liquid flood, the specific chemical composition, specifically the presence of fructose, creates a unique biological challenge. Standard glucose triggers a systemic regulatory response across the entire body. Fructose undergoes isolated, localized processing almost entirely within the liver. Now we will map the exact, unbroken biochemical cascade triggered when unregulated liquid fructose completely floods delicate hepatic tissue. This specific metabolic sequence engineers 2 distinct, measurable clinical endpoints: systemic hypertension and widespread obesity. Liquid fructose acts mechanically to alter vascular resistance. To understand the damage, we must shift our analytical perspective from traditional nutrition to rigorous pharmacokinetics. Absorption begins at the biological interface between the gastrointestinal tract and the hepatic portal vein. In nature, sugar is bundled within the matrix effect. When you eat a whole fruit, its inherent dietary fiber acts as a complex physical mesh. This dense fibrous mesh performs a strict mechanical function. It severely delays the stomach from emptying its contents into the small intestine. As digestion proceeds, that same matrix physically obstructs digestive enzymes, slowing down the rate at which they can cleave complex carbohydrates into simple sugars. Liquid soda lacks this protected solid matrix system. There is no physical fibrous barrier present to slow the descent. The resulting biological event is an instantaneous, unmitigated rush of free sugar molecules flooding directly into the hepatic portal vein. Stripping away the fiber matrix turns a regulated, slow-release energy source into a high-velocity molecular flood that the liver has no evolutionary mechanism to deflect. Following the flood from the macro-level portal vein down to the microscopic scale, we enter the interior of a single hepatocyte, or liver cell. This diagram illustrates cellular metabolism. Standard cellular glucose processing, known as glycolysis, operates like a highly regulated metabolic assembly line. Notice that pathway A features a distinct negative feedback loop. When the cell's immediate demand for energy is met, the system automatically halts the flow of incoming molecules. Fructose processing operates under a severe biological anomaly. It lacks an equivalent restrictive mechanism. The incoming molecules pour through the node continuously without stopping. The specific unregulated enzyme responsible for this initial processing step is fructokinase. Fructokinase aggressively phosphorylates the incoming fructose payload. Phosphorylation is the chemical addition of a phosphoryl group to a molecule, a necessary first step in cellular metabolism. Fructokinase performs this action continuously, regardless of the cell's actual energy requirements. While the glucose pathway halts itself when full, the unchecked fructose flow continues to force metabolism on every molecule it encounters. Because fructokinase ignores cellular energy limits, a dose of liquid fructose bypasses the primary biological safety mechanism against overconsumption. This unchecked fructokinase activity guarantees an immediate consequence: massive intracellular energy consumption. The rapid phosphorylation of the fructose flood aggressively burns through the hepatocyte's own critical reserves of ATP. ATP, or adenosine triphosphate, is the primary molecule used to store and transfer energy within cells. This diagram focuses on the chemical byproduct of that energy burn. When ATP is rapidly and unsustainably degraded, it generates a hazardous molecular waste product, uric acid. Simultaneously, the hepatocyte's mitochondria become completely overwhelmed, unable to process the volume of excess carbon substrates pouring into the system. The liver initiates an emergency response to this bottleneck, converting the excess carbon substrates directly into lipid droplets. This localized accumulation is defined as intracellular fat deposition.
It acts as a primary precursor to broader metabolic dysfunction. The hepatocyte's frantic attempt to process the liquid fructose flood bankrupts its own energy stores, engineering toxic byproducts and fat deep within the organ.
The newly synthesized hazardous uric acid completely exits the overloaded liver tissue, aggressively surging forward directly into the systemic bloodstream. We contract the damage to a cross-section of an endothelial cell, which forms the delicate interior lining of the blood vessel wall. These high concentrations of circulating uric acid physically interact with and bind directly to the vascular endothelium. By binding to this tissue, uric acid disrupts and inhibits critical endothelial machinery, specifically the localized production of nitric oxide. Nitric oxide is a soluble gas synthesized by the endothelium that regulates vascular tone. Nitric oxide serves a vital physiological role, acting as the chemical signal instructing blood vessels to remain flexible, relaxed, and dilated. When nitric oxide production is inhibited, the vessel walls suffer a severe mechanical consequence. They lose their elasticity, becoming stiffened and highly constricted. This forms the final causal link in the model. Unregulated hepatic fructose metabolism mechanically engineers systemic high blood pressure by biochemically destroying vascular flexibility. The central nervous system experiences a parallel site of systemic overload. A massive, rapid intake of liquid sucrose triggers a severe and abnormal dopaminergic response in the brain's reward centers. To protect neural circuitry from continuous chemical spikes, the brain initiates downregulation. Downregulation is the active reduction in the number of active dopamine receptors on a cell's surface, lowering its sensitivity to the stimulus. The physiological consequence of this downregulation is that the baseline threshold for feeling normal is raised, necessitating increasingly higher sugar doses to achieve stability. Just as the liver's metabolic pathways reach a breaking point under the liquid volume, the brain's survival hardware is actively rewired and degraded by it. This chart synthesizes the entire unbroken physiological chain of events initiated by high-volume liquid sucrose. We track the portal vein spike through unregulated fructolysis, triggering ATP depletion and uric acid synthesis, leading to nitric oxide inhibition and clinical hypertension. Adding dopamine receptor downregulation to the chart completes the map of systemic overload. This interconnected chain proves the true danger is the combination of rapid pharmacokinetics and unchecked biochemistry. This specific aggressive molecular combination targets and dismantles established homeostatic feedback loops across multiple distinct organ systems simultaneously. Liquid fructose delivered at this speed and volume overrides the body's standard nutrient processing. This substance acts as a dose-dependent pharmacological agent structurally equipped to bypass the human body's evolutionary defenses.
Thanks for watching Body Science School. Please like, share, and subscribe the channel for more.